So now we get into the more complicated sorting algorithms. And they're more complicated, but typically they're a little bit more efficient, which is why people actually use them. Now, when I say efficient, we'll get into more detail on that later, but as you remember, efficiency is measured in two ways in computer programming: speed and space. All right? So time and space, essentially. How long does it take to run, and how much memory is it taking up? So we'll get into more detail on that in future modules. But for now, what we're going to look at is this merge sort. And this merge sort is a recursive algorithm in actuality. And it's actually not difficult in concept, but it can be pretty challenging to actually implement in code. Essentially, the way it works is it will recursively break down the list until it gets down to a base case, which by all definitions is automatically sorted. And then it merges all those sorted elements together using almost an insertion sort type mechanism. So essentially what it'll do is it'll say, all right, looking at this list, find the midpoint. Now that's easy if you have an even number of elements, but in this case we have an odd number of elements. So if we take this number of elements, 5, and divide that by 2, then essentially what we're going to end up with is 2.5. But we can't have half an element. So we have to, if we're using integers, for example, the decimal just gets truncated off. So the midpoint would essentially be 2 elements. So that means that we break it off here. What do I mean by break it off? Essentially I mean creating 2 separate arrays. On this side we have 97 and -3. On the right hand side we have 5, 4, and 3. Well, what is our base case? How do we know when we're done splitting it up? Well, how do we know when a list is sorted? Well, a list is only sorted and absolutely sorted by definition in 2 cases. First of all, if the number of elements is equal to 0, if there's no elements, it's definitely sorted. Or the number of elements is equal to 1. One element is, by its nature, already sorted. There's nothing greater than or less than to it. So now we continue on with our merge because we can see that neither of these cases have satisfied the base case. So we look at this and we take this guy and we say, all right, let's divide it up even further. Find the midpoint. We see the midpoint is obviously 2 divided by 2. 2 divided by 2. And what we're going to have is we're going to end up with 1 element on each side in this case. So this gets divided up and we have 97 and -3. And now we go over to the other side and we continue on. But before we get that, we're going to build this back up, because as the recursion goes down, it goes down until we get to the base case. And once it gets down to the base case, it starts merging. So it brings things back together. And it says, all right, of these 2 cases, which one is less than and which one is greater than? So first of all, create an array that's equivalent size to all the elements that we're merging. In this case, there's 2 elements, so we have an array of 2 elements. Put the current smallest element that we're merging in the first element, -3, and then put whatever's left over on the right hand side. So 97. So far we've merged this piece, but we're not done over here on the right hand side. So this guy can't go any farther yet because it has nothing to merge with. So we got to go back over to this side. So on the right hand side, we find the midpoint. 3 divided by 2 is going to give us 1.5, or 1, because we don't have decimals in this case. So in that case, you're going to have a 5, and you're going to have a 4, and a 3. Now the 5 is definitely merged, but we have nothing to merge it with yet. So we have to keep dividing over here with the 4 and the 3. So we find the midpoint, and we end up with a 4 and a 3. Since both of these are base cases, we can now start merging. So we merge these 2 together. We create a list with exactly enough elements to satisfy our size. We say which one is less. Well, the 3 is less, and the 4 is larger. And now we merge with the branch of the next level up, because this is the recursion working its way back up the chain. So the 5 is merging with the 3 and the 4. Well, there's a total of 3 elements, so I'm creating a new array with 3 elements. And we look at it and say, well, what is the current lowest number? Well, 3 is the lowest number. So that guy's now used up. The 3 is now used up. So now we look at the 4 and the 5 and we say, well, which one's the current lowest number? The 4 is the current lowest number. That guy's now used up. So all that's left now is the 5. So the 5 gets put in place. So now we scroll down a little bit because we need a little bit more space. Again. And essentially what's going to happen here is now what we need to do, we need to actually merge these two pieces. So where you can see as we worked our way down, we kept dividing each arm or each branch of the split until we got to our base cases, and then we started merging each branch. So the left and right got merged, and then this right whole branch got merged with this left whole branch, and then we ended up with a result. So now this whole left hand branch is going to get merged with this whole right hand branch. So we look at the total number of elements. We have 2 on the left and 3 on the right, which means we're going to have 5 elements in total. We say, okay, well, which one's the current lowest number? Well, -3 is. So this guy gets used up, so we put -3 down here. Now it looks at the next lowest number. Is it 97 or is it 3? Well, 3 is lower than 97, so 3 gets put in. So 3 gets used up. Now we look at the next lowest number. Is it 97 or is it 4? Oh, it's 4. So 4 gets used up. Is it 97 or is it 5? It's 5. So 5 gets used up. 97 is the only number left over. So, as a result, we now have a fully merged and sorted list. You can see that we broke it down until we got to base cases here. We have a base case here, and we have base cases here. Whenever you see the base cases, that's when the merge starts to take place. So, it's really a 3-stage process. The first thing we do is we divide the list in half, and we continue doing so until we find the base cases, which is stage 2. Once we have the base cases, we begin stage 3, which is the merge process, merging the left arm, or the left branch, and the right branch to a newly formed list. And we continue to do this until we're built back up with a fully merged set. Now there's a lot of different implementations of a merge sort. Some of them will be able to actually merge it within the list itself without actually creating any new arrays. A simpler version, which takes up more space of course, is to actually have brand new arrays for each partition you create. Of course, this can be costly depending on how many elements you have in your array. So that is a merge sort.